In the absence of air resistance, all objects dropped near the Earth's surface fall towards the Earth with the same constant acceleration under the influence of Earth's gravity, regardless of masses. Around 1600, it was Aristotle who said that heavier objects fall faster than lighter ones. However, this was disproven by Galileo Galilei. According to the legend, Galileo observed that when he dropped two different weights simultaneously from the Leaning Tower of Pisa, it hit the ground at approximately the same time, regardless of their weight. So, also Galileo performed experiments related to rolling balls down inclines. And then Galileo rolled balls down slight inclines and he measured the distances that they covered in successive time intervals. So he used an incline so that the acceleration of the balls will reduce, which makes it easier for him to measure time intervals. And he gradually increased the slope of the incline and he was finally able to make conclusions about freely falling objects that are falling along the vertical axis. So you can do a similar experiment. So if you have time, you get a piece of coin and you get a paper. You drop the coin and paper simultaneously, and you will notice that the coin will always reach the ground faster, right? But if you crumple the paper into a tight ball, and you repeat the experiment, you will find that both the paper and the coin will hit the ground at the same time. This proves that no matter the mass of the object, that the acceleration is the same for all objects, at least near the Earth's surface, and if air resistance is negligible. In fact, there was also an experiment done by David Scott. He's an astronaut. Back in 1971, when he went to the moon, he released a hammer and a feather at the same time on the moon, and he found out that he discovered, I think there's a video here. There's a video in YouTube about this. But both objects fell together, the feather and the hammer. Oh, okay. But just to be clear, when we're talking about freely falling objects, we're not limited to objects that are dropped from rest. Any object that is moving under the influence of gravity alone, regardless of its initial motion, can be considered free fall. For example, if you throw the object upwards, you throw the object downwards, something like that, or you just drop the object. Once you release the ball, the motion of the ball is purely under the influence of gravity alone. So, when it comes to freely falling objects, the value of G, actually, the value of acceleration is 9.8 meters per second squared, directed downward. That is near the Earth's surface, 9.8 meters per second squared. We call that a G. And sometimes we approximate G to be equal to 10 meters per second squared. But in reality, the higher you go up the Earth, the acceleration reduces. But for our purposes, let's just stick to problems near the Earth's surface so that we stick with the constant acceleration. So, of negative 9.8 meters per second squared, the negative sign indicating that the direction is downward. Okay, moving on. Let's answer this now. What happens to the acceleration of a ball after it is thrown upward into the air? Does the acceleration increase, decrease, increase and then decrease, decrease and then increase, remains the same? What is your answer? Well, the correct answer is remains the same. Thing is that the for the entire time interval that the ball is in free fall, the acceleration is that due to gravity alone. So constant. The acceleration is negative 9.8 meters per second squared downward. How about this? What happens to the speed of a ball after it is thrown upward into the air? So A, increase, B, decrease, C, increase and then decrease, D, increase, D, decrease and then increase, E, remain the same. What is your answer? So the correct answer is letter D. So while the ball is rising, it is slowing down. After reaching the highest point, the ball begins to fall and its speed increases. So that's because on the way up, the direction of the velocity is upward, but the acceleration is downward. And every time the direction of acceleration is opposite the direction of velocity, the object's velocity will decrease. But as the ball reaches the highest point, it will begin to fall, and this time the velocity direction is the same as the direction of acceleration due to gravity. That's why, since the directions are the same, for velocity and acceleration, the velocity shall increase. Let's look at this conceptual example. A skydiver jumps out of a hovering helicopter. A few seconds later, another skydiver jumps out, and they both fall along the same vertical line. Ignore air resistance so that both skydivers fall with the same acceleration. Does the difference in their speed stay the same throughout the fall? Does the vertical distance between them stay the same throughout the fall? Well, the answer is the difference in their speeds remain the same throughout the fall, and the first skydiver covers a greater distance than the second, therefore the separation distance between them increases. Now let's look at some word problems. So a stone thrown from the top of a building is given an initial velocity of 20 meters per second straight upward. The stone is launched 50 meters above the ground, and the stone just misses the edge of the roof on its way down as shown in the figure. So you probably have experience dropping objects or throwing them upward and watching them fall. So this is probably experience that is familiar to you. If you want, so you can try to get a small object right now and toss it upward and notice the time interval required for it to fall to the floor. Now imagine that you're on top of a building and you're throwing the object upward from the roof of the building. Something that I strongly don't recommend. Well, the stone is in free fall. We are neglecting air resistance. So we need to model this problem as a problem for a particle under constant acceleration due to gravity. So we use the equations that we learned last meeting about the kinematic equations, but instead of using x subscripts, we use y subscripts because this motion is vertical. And we already have our value for acceleration along y, which is negative 9.8 meters per second squared. So using PA equals 0 as the time the stone leaves the thrower's hand at position A, determine the time at which the stone reaches its maximum height. So if you look at your equations, you can use this, no? This equation, Vy final. Notice we're using y subscripts because the motion is vertical. Vy final is equal to Vy initial plus Ay times time. So why are we using this equation? Because we are given the initial velocity, which is this one is 20 meters per second. Yeah, 20 meters per second. And this one is given as well. This is free fall. So expect that this is negative 9.8 meters per second squared or negative g. G is our symbol for 9.8. Vy final is given. This is 0. How do we know that for the problem being asked, the final velocity is 0? How do we know that? Because we're considering the situation wherein the stone reached maximum height. And we're asked for the time, so this is the perfect equation to use. We just isolate the variable t, and then we substitute values. And we get that the stone will reach a maximum height of 2.04 seconds. Find the maximum height. So, the stone above the initial position. So if we treat our initial position to be equal to 0, right? Our maximum height, y max, is equal to yb, and that is equal to this kinematic equation. C, point A and point B, right? And this is the formula. You will see this in our list of kinematic equations. But we use this because we are given the initial position, which is 0, because we just defined our initial position to be y equals 0. And this is supposed to be Vya. There's a typo here. But this one is 20 right here. This is 20 meters per second. And the time, we already solved for how long the stone reaches maximum height. I think 2.04 seconds. Yeah. And so this is the perfect formula to use. Acceleration, of course, is negative 9.8. So, and time again, we can solve for the maximum height. We had to use 2.04 seconds because we are interested in the height at that time. Determine the velocity of the stone when it returned to the height from which it was thrown. Okay, well, if it was, I'm just gonna say, if it was thrown at a velocity of 20 meters per second upward, as it goes back down and reaches the same level from, or same height from which it was thrown, it will now have a similar value of velocity, but the direction is opposite. So what I'm saying is the answer for this problem should be negative 20 meters per second. So this is the solution. And what he did is, what is VYC? Yeah, VYC here is defined as same level as C is the point, which is the same level as the point A where the ball was thrown. And Vya, this one is the velocity at which the object was thrown. A here, Yc minus Ya. Well, Ya is at 0 and Yc is also at 0. So you have now byc squared equals 400 meters squared, and we actually get the square root of 400 here, but remember that square roots always have a plus minus, and you choose the one which has a minus sign. Square root of 400 is 20, so the answer is plus minus 20. You choose the answer with a minus sign because you know that the ball's direction is downward at point C. Find the velocity and position of the stone at t equals 5 seconds. Okay, we can use our formulas, and this one will give you that the velocity at 5 seconds. We just substitute 5 here for t, and the initial velocity and acceleration that will give us negative 29. So at 5 seconds, the ball is already moving downwards. And the position, you can use this formula. Negative 22.5. The negative position indicates that this position, the ball is below the starting point. Okay. Well, that's all. And thank you for listening. How do I stop recording?